Очень рад, что могу перед вами выступить. И, конечно, огромная благодарность организаторам конференции. Я знаю, насколько это все было сложно. Вот, спасибо еще раз. И я очень хотел сделать доклад по-русски, но, наверное, все-таки придется делать по-английски, поскольку есть онлайн некоторые англоязычные участники. Хорошо. So the topic of my today's lecture is mathematical modeling of respiratory viral infections, and it's a joint work with many collaborators listed here, and I'm very happy to list my collaborators from these Rudan universities, in particular, Anastasia Mazokhina, Daria Neverova, Vladimir Popov, Alexey Tokarev, and also mention some other people, Nikolai Bessonov, my long-term collaborator, Gennady Bocharov, with whom we work on these topics during many years. So about viral infections, so you see here the slide about history of viral infections. In fact, they started many years ago. Epidemics of viral infections started thousands of years ago when people began to live together in these agricultural communities. And then during the whole history, of course, sometimes in some periods, epidemics of viral infections played quite an important role. And 12,000 years later, we are all, of course, concerned by this epidemic. This is what I'm going to discuss a little bit today, how to understand all that, how to model these epidemics from the immunological point of view and epidemiological point of view. It will be a short overview of recent works. And of course, talking about mathematical modeling, we should take into account that this is a very complex problem, multi-scale problem with very different time and space scales. In particular, it's viruses, very small, tiny particles, and then human organism, and then the whole population. And there are many questions related to that, in particular, how infection spreads in cell culture, of course, immune response, virus mutation, and so on. And I will, at the end of my presentation, I will talk about a little bit about this question, immunoepidemiological models. So this is what I'm going to discuss briefly today. How infection spreads in cell culture, about emergence of new virus variants, another very important question, as we know now. Then about competition of different virus variants, and finally, very shortly also about some questions, how infection spreads in the population. I will begin with a very short biological introduction. We know that viruses, these are small particles, they cannot reproduce by themselves. They need host cells. So virus penetrates the host cell, its genetic material, RNA or DNA, integrates the nucleus, and then there are new viral particles appear here. And one host cell can produce hundreds and even thousands new viral particles, and sometimes cells die after that. On the other hand, our body responses in different ways. There is a part of the immune response called innate immune response and also adaptive immune response. And finally, at the end of that, there are different lymphocytes called T lymphocyte or cytotoxic T lymphocytes, which kill infected cells, and also B lymphocytes, which produce antibodies, and these antibodies neutralize viral particles. And of course, all these questions are studied experimentally, and also there are many clinical studies. In particular, there are many studies about propagation of viral infection in cell culture, as it is shown here, or in tissues, or in particular ex vivo tissues. So there are many experimental data, and we will discuss some of them today. So we'll begin with the very first and basic model of viral infection to understand, in fact, what happens how to describe, how to understand viral infection. By the way, just to mention that mathematical models in immunology appeared not so long ago. If first epidemiological models like Bernoulli was 18th century, first immunological models appeared much later, and in particular in the Soviet Union, it was Guri Marchuk at the same time in the 70s, 1970s, at the same time in the United States, Jonathan Bell. And Guri Marchuk created scientific school, continued it now with his younger colleagues, in particular Gennady Bocharov, with whom we collaborate. So this is the very first and maybe the simplest model, immunological model, well, not immunological, sorry, simplest model of viral infection. And I will explain what it is because it is very simple and we need to understand what happens there. And in fact, here we have three variables. U is the concentration of uninfected cells, W, the concentration of infected cells, and V, the concentration of virus. So virus, so we have here the term minus UV, it's how virus infects uninfected cells. So the same term is here, so we have this infected cells after that. And then infected cells produce new viral particles. So this is basically, and then there are death terms and this term here. So this is the simplest model describing viral infection. And what happens here? So we see here these numerical simulations and this figure done by the colleagues present here. So we see that the concentration of uninfected cells, its red line, it decreases. The concentration of infected cells, it decreases and increases and then decreases, and also the same for virus. It's this green line starts from 0, grows, and then also decreases. Even in this very simple model, we can already obtain some, I would say, important results. In particular, we can introduce this virus replication number. It's a parameter which determines whether this infection will develop or not. This is similar to basic reproduction number in epidemiology. So if R0 is larger than 1, then infection will develop, otherwise it will not. And another important parameter is viral load. Here it is the integral of this virus concentration, and we'll see below that this is important because it determines the infectivity of infection of virus, and it can also be found analytically. So the next step, we introduce the space variable because we want to study how this infection spreads in cell culture. So it is the same model as before, but we have now this virus diffusion in the extracellular space. We can have also this time delay here because there's time delay in replication. And then if we do numerical simulations, we obtain something like this shown here. So as before, this blue is the concentration of uninfected cells, then infected cells, and this virus. And this whole structure propagates in space in cell culture. So this is how infection spreads in cell culture. And from the mathematical point of view, such solutions are called reaction diffusion waves. These are functions which depend on this combination of variable x minus ct, where c is the wave speed. If we substitute this solution in this form of the equation, we obtain this system of ordinary differential equations, and we can study different mathematical equations such that the existence of such solutions, the stability, the speed of propagation, and some other. And talking about reaction diffusion waves, it's a very developed theory which starts with famous works by Kolmogorov, Petrov, Piskunov, and Fisher in 1938. Then many other works. I also worked on that, and there are many mathematical questions behind related to elliptic and parabolic problems, spectral problems, and other questions. I will not discuss them today. But we can use this theory and we can study these questions. In particular, well, under some additional simplifications, if we neglect the death of infected cells, we can reduce the system of 3 equations to the system of 2 equations. And this is a special class of parabolic systems. They are called monotone systems. And there are some mathematical methods based on maximum principle, which can be applied now. And we obtain such kind of problem as written here, and we can study existence of such solutions and their stability. And we can also find the speed of propagation written here. Well, of course, there are many questions related to that, because as we know from the theory of reaction diffusion waves, sometimes such solution can be unique. In some other cases, they are not unique, and this is called what is called minimal wave speed. And exactly in this case, we have this minimal wave speed given by this formula. Why it is important? What is the biological meaning of speed of propagation? This is related, so we can think about what happens in our body. So infection spreads in the tissues of our body, in particular in the lungs. So the speed, the spreading speed determines the part of the infected tissue, in particular of the lung. For example, here you see this lung damaged with this COVID infection. In these yellow areas, it's the part of the tissue damaged by this infection. So the part of this damaged part it is determined by the speed of propagation. So it has a clear biological meaning, quite important. So the second important characterization is related to viral load. We previously introduced this viral load as an integral with respect to time. Now let us consider this integral with respect to x variable as a function of time. So this means that we have our cell culture or cell tissue, and this integral means the total quantity of virus in this culture at some given moment of time. Then we can consider it as a function of time. If we do that, for example, in numerical simulations, we'll obtain such curves, this blue curve shown here. So in the beginning, the concentration decreases because of the time delay in virus replication. Then there is this rapid explosive growth when infected cells begin to reproduce virus. And then there is this last stage where it is more or less constant. It is exactly this wave propagation. And well, I will not discuss it now, but we can use different analytical methods to determine this viral load and or approximate it, like you see, for example, here, this green line is obtained analytically, and also this red line, so we can find viral load. Why viral load is important? Because if we talk about respiratory viral infections, so viral load in the upper respiratory tract determines the infectivity of this virus. So this is also important characterization of viral infection. So what we can conclude from this first part of modeling is that infection propagates in cell culture or in cell tissue as a reaction diffusion wave. We can determine the wave speed, which correlates with symptoms, and we can determine viral load, which correlates with infectivity of this virus. And we see that there are 3 stages of infection progression. So what happens in the experiments? This is an example, this experimental work done about 15 years ago for the first SARS-CoV-1, not SARS-CoV-2. So, and here it's experiment, it's culture of epithelial cells, and here is how viral load depends on time. So we can compare our modeling with these experimental results. In fact, here there are 2 different viruses, poliovirus and SARS-CoV-1, and we obtain so this red dots experimental results and curves this numerical simulation, so we can feed this data, the parameters, and we can approximate this experimental data. And now this is already for SARS-CoV-2. So as before, these dots are experimental data and curves are numerical simulations. And here we have two different virus variants. So not written here, but red is for Omicron, blue is for Delta, and at the left it is for epithelial cells, and in the right for lung cells. And as before, we can determine the parameters of, so these are data for the viral load. So we feed the data and we find the parameters of the model. And when we find the parameters of the model, we can determine the speed of infection spread. So this is a construction we use. We have experimental data. We feed this data, experimental data for viral load. We feed this data with modeling. We determine the parameters of the model, and then we can find the spreading speed. So what we obtain in this case, if we take, for example, epithelial cells, and Omicron, it's red line here. So it appears that in epithelial cells, the spreading speed of Omicron is larger than for Delta. So epithelial cells in particular upper respiratory tract. So in upper respiratory tract, Omicron spreads faster than Delta. This is, for example, in particular because of that incubation period for Omicron is shorter than for Delta. And if we take lung cells, it is opposite. Spreading speed for Delta is larger than for Omicron. And because of that, symptoms for Delta, in particular, how this disease develops in the lungs. For Delta, spreading speed is larger, and so as we discussed before, symptoms are more severe. The next question I'm going to discuss also very shortly, it's about the emergence of new virus variants or virus quasi-species, depending on context. And of course, it's also a very big and very interesting topic, and starts with Darren works on the emergence of biological species. Of course, viruses are not biological species. Sometimes they're called quasi-species. But the same ideas or something similar, which was used to model biological evolution, can be also used to model the evolution of virus quasi-species. And this is an example of this evolution of this SARS-CoV-2. In some sense, we can call it phylogenetic tree, so how different variants appear here. And this part of the work, it's our recent works with colleagues listed here. So we start with the same model as we just previously discussed, but now we introduced also the immune response, and immune response here is considered in a very simple way, and of course it is done deliberately because otherwise the model would be much more complex. So this C here is the concentration of immune cells, and the well, their proliferation, their quantity depends on the antigen, so on the concentration of virus with some time delay, and then these immune cells, if we talk about, for example, cytotoxic T lymphocytes, they kill infected cells, so we have this term here, or if we talk about antibodies, so they neutralize virus, so we have this term here. So the next step of the construction of this model, we introduce this X variable, but at this time, X is not physical space, but this is the space of genotypes. So we consider viruses with different genotypes. And this diffusion term corresponds to virus mutation. Another important remark here is that now how this, if we describe how immune cells act on virus, we should take into account also this difference in genotypes. And we have this now integral term here, and this integral with this kernel shows how the efficiency of the immune response, how efficient are these immune cells eliminating virus depending on the respective genotypes. So in some sense, in particular for the adaptive immune response, so immune cells are adapted to kill or to neutralize virus with certain certain antigen. If there's a difference in antigens, so the efficiency of immune cells can be less, and this is why you can have this. We have this integral with this kernel here, and this is very important. This is what is called cross-reactivity in the immune response, and if this difference is large, so phi, in particular, we consider this function phi is a finite support. So if this difference is large, then these immune cells cannot eliminate virus with very different genotypes. And because of that, this is okay. Because of that, so it is called immune escape. So virus tries to escape the immune response, and this is finally how this new virus variants will appear. But from the mathematical point of view, we do some analysis of this model, in particular stability analysis. What we obtain here, so in particular in this diagram, so we have here this X variable, genotype variable, here time. In the beginning, we have all antigens localized here in some interval of genotypes. During some time, it stays here, but after some time, we see that virus with different genotypes appear here because of this immune escape. So this is one of possible, not the only mechanism, but one of possible mechanisms how new virus variants can appear. So once we have different virus variants, they can begin to compete with each other, because we remember that virus cannot reproduce by itself. It needs host cells to reproduce. So virus begin to compete for host cells. So we consider the same model as before, but now there are two viruses and two types of infected cells. Otherwise, it is the model similar to the model. So what happens here is there are two viruses in the same culture or in the same tissue. They begin to compete with each other. So what will happen? In fact, what we obtain that one of them will win this competition and will eliminate another one. So which of them wins the competition? And the answer I formulate here in the term of informed mathematical position or theorem, but we cannot prove this mathematically. We obtain this in numerical simulations, and the answer is quite clear that if you have two competing viruses, then for each of them, we determine the spreading speed. We discussed it before. So the virus with larger individual spreading speed will win this competition and will eliminate another one. If we return to this SARS-CoV-2 with two variants, Delta and Omicron, we take epithelial cells, then we discuss that Omicron larger spreading speed. So in the culture of epithelial cells, Omicron will eliminate Delta, and in the culture of lung cells, Its opposite, delta eliminates Omicron. This is what is observed in the experiments. It's exactly this experiment which was done in the opposite order. First, there were experiments, and this experimental results, in fact, inspired our modeling, but the result is exactly the same. So here at the left, it's culture of epithelial cells, human epithelial cells, and here Omicron, it's this diagram, it's violet, it's eliminate delta, and in the lung cells, it is opposite, delta eliminate Omicron. Well, in the last part of my presentation, I will discuss this question about some immunoepidemiological models, so we can use these immunological models we discussed just before to study how infection spreads in the population. And of course, when we discuss how infection spreads in the population, we should begin with well-known models for many years, compartmental models such as SIR and similar models shown here. Well, here S is susceptible population, I infected population, and R recovered. So susceptible, the susceptible times infected gives the rate how susceptible become infected. Then infected can here become recovered or can die. So this is the classical epidemiological model. But what is important here is that one of the assumptions of this model is that this recovery rate, this is interesting, this recovery rate, how infected become recovered here. So the recovery rate at time t is proportional to the number of infected at time t. This is strange because, well, for example, we want to determine how many recovered we have today, but it is not, we should not take the number of infected today because this disease has some duration, for example, 2 weeks. So we need to take the number of infected 2 weeks ago. Then we can determine how many recovered we'll have today. So this is really, of course, everybody understands that, but still everybody can consider this model. But there is a fundamental problem with such kind of models because it does not take into account the duration of the disease. Just, for example, 2 weeks difference, it's very important because during the exponential growth, I of t, the number of infected today or 2 weeks ago can be very different. Well, and of course, I consider here this SIR model as an example, but it's the same assumption in all usual epidemiological models. So what should be done, in fact? We should take into account the disease duration and this recovery rate. So this is what is shown here. For example, at time 0, so there are some populations, a number of people were infected at time 0. So what is the proportion of them which will recover during all these days, 1, 2, till whatever, 15, 20 days? Yeah. And this data are available. So the recovery rate is a function of time after infection. So this is more or less a curve like this is recovery rate, and this is death rate. And now, if you have this dependence, this distributed recovery and death rates, so we can determine the recovery rate in time t shown here. So in fact, it becomes this integral shown here. J of iter is the number of people infected at this time, iter. So we take this time difference between t and iter and this recovery rate. So this integral gives the recovery rate. Same with death rate. So this is, in fact, how this epidemiological model should be considered to be more precise. So this is what is written here with this distributed recovery and death rates. But I introduce also here this another integral. In fact, this integral is infectivity rate. Infectivity rate is also distributed because we know that we discussed before, infectivity rate depends on viral load. Viral load is a function of time. So this is why we have also this integral here. And what I wrote here, time-dependent infectivity is proportional to viral load, and there is this constant here, this proportionality coefficient. We don't know it, but we'll determine. So in fact, instead of the usual SIR model or such kind of models, we have now this integral differential equations with distributed infectivity, recovery, and death rate. If we want to be more precise, we should take into account also, of course, vaccination. And I don't have time to discuss it in detail, but so we can introduce immunity of the population, taking into account how many people were vaccinated as a function of time, and how long they preserve immunity after the vaccination, and how long they preserve immunity for those who were recovered. What is important here is that we have all this data. We know how many people were vaccinated. We take just this data, easily available. And we know how many people were recovered. This data also available. What is a little bit more difficult is to determine this immunity, how long this immunity continues after vaccination or after recovery. But these data are also available. Well, when we did this work, it was already several months ago. But this data maybe was not very precise, so we used at the time data we had. So we'll see what we obtain with that. So now we have what it is called data-driven model. So we have this model with distributed all these parameters, recovery and death rates and infectivity rates, immunity of the population, and we take all this data about vaccination and recovery. And well, because all that country dependent, so we did it for France. So what we have here, you may remember that I mentioned there's one unknown parameter. We know in this model, we know everything except for one parameter, which is the proportionality coefficient between viral load and infectivity. So what we do here, we take 2 weeks in December, and this green line, it was fitted, simulations fitted to approximate this data. So this black dots here, it's daily cases, new daily cases taken from the data, epidemiological data. So we take this black dots here, and we find this parameter k, this proportionality coefficient, fitting this curve here. This is the only fitting we do here in this curve. So then the next one is this validation, model validation. It's this blue curve. So this work was done here in March. So we took this interval from January to March. And so this blue curve, numerical simulation, black dots data, and we see that we obtain quite good approximation here. But then we continue this curve, this red curve now. It's our prediction how this epidemic will continue after that, after March, right? So what, this is data now, how this epidemic, new daily cases in France now. So this big first outbreak. It's this one. It's the end of last year. It's Omicron. Then in the spring, we see now this. We compare this red curve here. I forgot to tell you that this different 1, 2, 3, 4. It corresponds to different vaccination strategies, right? So we take this just one, no vaccination. In fact, vaccination was basically stopped here, and number of new vaccinated people is very low. So in fact, we take this curve, this first curve. After this first large outbreak in December, January, so there's this decrease here, this new wave in the spring, and we obtain it. It corresponds to our predictions here, and then another. Well, it stops again, it decreases again. So this new wave here begins in June, in fact. So this is how it is now. So, and it corresponds to this new wave shown here, and we are somewhere here in the middle of this new, epidemic wave. So we obtain quite good description of this epidemic progression with this immunoepidemiological model. In fact, it works more or less. Well, of course, the numbers are a little bit different. So we give quite precise estimates of this new wave. So the date is more or less the same at the beginning of June, but the numbers are a little bit different. So our prediction is larger than it was here. For this new epidemic wave, so we don't know yet, we are here in the middle. Okay, so to conclude all that, so what we have, we discussed this that infection spreads in cell culture as a reaction diffusion wave, that the spreading speed correlates with severity of symptoms and viral load with infectivity. We see that this experimental data on different variants responds to what we obtain in this modeling. We discussed some models of the emergence of new virus variants. And finally, we see that these immunoepidemiological models give quite a relatively accurate prediction of epidemic progression. Well, there are a number of other studies, particular presented immunodominance. So what we study now, it's how, this is also important question because it's respiratory viral infection, how this infection spreads in bronchi, and this is related to mucus motion and to lung obstruction, and also some other questions. These are some publications, recent publications. Well, acknowledgement, of course, this works were supported by different programs and grants, in particular in this Roden University, and also our Center on Mathematical Modeling in Biomedicine. So I would like to finish. We should everybody stay healthy. Thank you very much.
Раз. Дорогие коллеги, есть ли вопросы?
Раз. Вот вы рассматриваете детерминированные модели, очень хорошие, красивые, но если взять процесс распространения вируса, то на него оказывают влияние различные случайные факторы. Вот вы считаете, что ими можно пренебречь, или все-таки в некоторых случаях их бы хорошо как-то учитывать?
Понятно, спасибо. Несомненно, было бы хорошо их учитывать, особенно если понимать, откуда они берутся и что они означают. Наверное, есть разные случайные факторы, которые могут проявляться. Я согласен, что было бы хорошо, конечно, их в той или иной степени учитывать. Наверное, это можно рассматривать как дальнейшее развитие этих работ. Да, спасибо.
Скажите, пожалуйста, вот вы, когда рассматривали омикрон и дельту в легких и эпителии, и вот графики эти показывали, ну, сейчас у вас графики по омикрону и дельте одинаково выглядели, то есть омикрон был всегда больше, а вы говорили, что наоборот дельта побеждает в легких. У нас
Да,
чего
это любопытный вопрос, как раз мы
вот, да,
с Алексеем, по-моему, его обсуждали. Вы понимаете, вот здесь показана вирусная нагрузка. Это графики для вирусной нагрузки. И вот здесь, допустим, в начале у омикрона вирусная нагрузка больше, потом становится меньше. И эта разница довольно существенная. Омикрон начинает проявляться быстрее, задержка по времени для него меньше, и поэтому скорость его распространения больше. Вот получается так, что несмотря на то, что потом вирусная нагрузка у него меньше, но все равно скорость распространения у него больше, потому что вот у него здесь такой запас большой получается. А вот в клетках легких, несмотря на то, что он немножко раньше все-таки начинает проявляться, но этого недостаточно, и все-таки потом дельта побеждает. То есть здесь, понимаете, уже получается довольно такая тонкая игра на числах. Нет. Площадь под кривой – это очень такая интересная медицинская характеристика, которая называется area under curve. Они не называют это интеграл, они это называются area under curve, и даже такая аббревиатура из трех букв. Это действительно вот, площадь под кривой, которая как-то коррелирует с заразностью этой инфекции. Но, вы понимаете, вот это то, что, может быть, я не успел или не смог достаточно хорошо объяснить, что есть две разных характеристики. Одна характеристика – это вирусная нагрузка, другая характеристика – это скорость распространения. И они могут коррелировать, а могут не коррелировать. То есть, понимаете, можно какой-то вариант может иметь большую вирусную нагрузку, то есть быть более заразным, но при этом иметь меньшую скорость распространения и, соответственно, иметь менее суровые, ну, в общем, менее сильные признаки заболевания. И это то, что как раз наблюдается для омикрона дельта. То есть это относительно независимые характеристики, хотя, конечно, поскольку они выражаются через те же самые исходные параметры модели, конечно, они не полностью независимы.
Есть ли еще вопросы? Есть вопросы онлайн?
Can you hear me? I have the following question to you. I'm very much interested in the spread of the virus. Especially to my knowledge, I have no model seen for the spread in the body for different organs, which would be very important. And one problem which I see in modeling, even in the tissue, is the binding, because the binding of the virus depends on the availability, for instance, of ACE2. And this is differently distributed, and it should, don't you think it should be put in the dynamics? My question is, how is the experiment made in the tissue? Because I think this binding is very important.
Yes, this binding is very important, and implicitly it is taken into account in the model through the parameters of the model.
Yes, but they are dynamic too. ACED distribution is also dynamic.
Well, so for example, here this coefficient A, well, in some sense, it is,
It's changing.
well, it corresponds, well, it describes how this virus penetrates cells, in some cells. Of course, it's a very simplified model. There are more detailed models, but it's a very simplified model. It correlates with this parameter, and of course, all this dynamics depends, basically depends on two parameters. This parameter A and this parameter B. Right. Yes,
I think the A has to be put, the dynamics in the evolution should be put in, also the dynamic of the bindings. The ACE2 is very important, and it's a dynamic factor too.
Yes, yes. And also, well, of course, also time delay here. Well, time delay, it's basically a delay in replication, but in some sense, it can be also correlate with time delay in binding and cell penetration.
But your experiments are made in what kind? Just a normal epithelial layer or a tissue, or what is done in the experiments, which you refer?
Well, I'm not sure that I understood, because there are some problem with sound, some problem of hearing, I don't know. But concerning the experiments, these are experiments with different cell types. In fact, these are the experiments. This works. There's 2 or 3 of them published in the beginning of this year, in January and February, for different cell types. And in particular here, it's 3 types of cell cultures. Oops, sorry. This human, what? No, I'm trying to remember what means A. Anyway, human epithelial cells, and the last one is human lung cells, and this is some other cell culture.
Because I'm asking this question because we are studying this not with the viruses, but with immune cells, with neutrophils. And you have to expect some new problems coming up in real cell cultures for the movement of cells and probably of the virus in the cell cultures. Okay, if you have, I would be highly interested getting more information outside of this lecture now. Maybe you can mention what they did in the email to me. Thank you. Thank you.
Yeah, thank you very much. Yes, I will.
Thank you very much. Are there any questions or comments? Тогда перерыв 7 минут. You can already share your screen and maybe turn on your microphone. Have needed access to this. Can you hear us? Yes, we can see your
Your microphone switched off. Can you switch on your microphone, please?
Yes, we can see your presentation. Also, maybe you turn on your. Cannot hear you. Hi. Could you please say something? Dear colleagues, so it's time to start next talk. Paul, can you hear us? Because we can see you, but unfortunately we cannot.
Okay. Am I audible?
Okay, excuse me. So let me introduce our next speaker from India, from University of Kalyani, Professor Paul. So
Thank
please.
you. First of all, I'd like to thank the organizer for giving me this opportunity to present my work. The title of my talk is Role of Space in an Eco-Epidemic Predator-Prey System with the Effect of Fear and Selective Predation. In this talk, we like to explore the effects of fear and additional foods in an eco-epidemiological system subject to selective predation of predators, and to investigate the effects of diffusion on the interactive dynamics of prey and predator with combined effects of fear, additional foods, and selectivity. This is the brief outline of my topic. First, introduction, the temporal model, and the mathematical analysis of temporal model, and then spatiotemporal model with stability analysis of the spatiotemporal model and numerical simulation. And we also like to observe the different types of pattern formations and at the end discussion. First, I'd like to give a brief introduction about this kind of model. We all know that parasites play a prominent role in trophic interaction and strongly influence the food web's characteristics. It can also manipulate the potential of its host and affect the abundance of predators. This is, of course, prey-predator type model with infection in prey population, and predators' preferences play a prominent role in the predator-prey parasite system and strongly influence the food web characteristics. And it has been observed that the predators tend to forage the prey that have high parasite burden. And for prey species, the susceptibility to potential predators creates a spontaneous reflex of physiological stress, and to adjust with this perceived risk of predation, the prey population adapt several strategies such as alteration in habitat uses, aggregation pattern, foraging activities, and hours of vigilance, reproductive strategies, etc. And under resource limitations, predators may deviate from their usual diet and exhibit some inclination towards the alternative prey items to support their survival. And for this, the concept of additional foods provided to the predator species always are beneficial for their survival in the ecosystem. And in fact, providing additional foods enhances predation on the target prey and hence increases predator population, which in turn reduces the prey population. Spatial patterns are usually observed in nature and can alter the specific temporal dynamics. After the work of Turing, several mathematical models have been investigated by considering the role of space. And predator-prey interactions generally occur due to a wide range of spatial and temporal scales, and spatial components of ecological interactions play an important role in shaping the ecological communities. Here in the present work, we consider an eco-epidemic predator-prey mathematical model with infection in the prey population only, and the fear of predators is assumed to reduce the reproduction of susceptible prey and disease transmission also, and additional foods supplied to the predator species. And the predators can distinguish between susceptible and infected prey and prefer the former, that is, they prefer susceptible over the infected one, and or vice versa. And the aim of this study is twofold. First one is the explore the effects of fear and additional foods in an eco-epidemiological system subject to selective predation of predators, and investigate the effects of diffusion on the interactive dynamics of prey predator with combined effects of fear, additional foods, and selectivity. We'll address the above mentioned ecologically important questions by investigating the models with and without diffusion with mathematical as well as numerical techniques. And this is the first one, our temporal model. Here we have N and P denote the densities of prey and predator population in an ecological community at any instant of time t, and due to infection, prey population is divided into two classes. One is susceptible one and another one is the infected one. Here we assume that this is the growth of susceptible population. R0 is the birth rate of susceptible prey in the absence of fear. And due to fear of predation, the birth rate of susceptible prey get reduced and decreased by the factor R0 S over 1 plus K1P, a decreasing function, the cost of fear and density of the predator population. And this is the death of susceptible population, susceptible prey, and this one is the crowding effect of the susceptible population. And here we assume that this is the due to infection. This is lambda is the rate of transmission from susceptible to infected class, and the effect of transmission rate takes the form this lambda Si over 1 plus K2P, where lambda is the rate of infection and K2, this K2 represents the level of fear of predators. The infected prey, this one is the infected prey, is assumed to recover from the disease at a constant rate gamma. And also due to this is the predator population, due to supplied additional foods, the predator follows logistic type growth rate, with R is the intensive growth rate and K is the carrying capacity of the population. And predators assumed to predate both on susceptible as well as on infected prey population. And we consider multiple prey type 2 response function, this NSP over B plus S plus theta I and N theta IP over B plus S plus theta I for the predation of susceptible and infected prey respectively. And the parameter theta, this parameter theta is the most important one here, quantifies the selectivity or preference of the predators to infected prey over the susceptible ones, or vice versa. If theta is greater than 1, predators prefer infected prey, and if theta is equal to 1, represents equal preference to both susceptible and infected prey. And if theta is in between 0 and 1, tells that the predators prefer the susceptible prey. And this mu is the death rate of infected prey, which also includes the death of infected prey due to natural mortality as well as virulence of the disease. And this delta is the natural death, and this nu is the crowding effect for the predator class. And this is the values of parameters for our numerical simulation, and also the description of model parameters. I have already described all these parameters, and these are the parameter values, and this is the units. For equilibrium analysis, we see that the population free equilibria A0, which always exist, and the susceptible prey only equilibria is this one, and there is another equilibria with predators only, because predator has logistic growth rate, and this is the predator prey equilibria. And these are some and this is the coexistence equilibria, E star, S star, I star, and P star, and P star and A star, I star are given by this relation. And for stability analysis, we have calculated the eigenvalues of the Jacobian matrix evaluated at each equilibrium point. And I'm not going into details of this stability analysis, and we are mainly interested in the coexistence equilibria. Yeah, this one. This is the for the for the coexistence equilibria. These are the entries of the Jacobian matrix, and the corresponding characteristic equation is obtained is this cubic equation. And by using the Routh-Horowitz criteria together with this equation, we have the following theorem that the equilibrium point E star is locally asymptotically stable if this coefficient is A1, A3, and A1, A2 minus A3 is all are positive, and for Hopf bifurcation analysis, we present the following theorem regarding the existence of Hopf bifurcation, and by considering the preference of selectivity, because this parameter theta is one of the most important parameters in our model system. And the necessary and sufficient condition for the occurrence of Hopf bifurcation from the coexistence equilibrium E star is that there exists theta is equal to theta bar, such that this A1, A2 minus A3 at theta equal to theta bar is equal to 0. And this one is the transversality condition, that is the tangent at this point is not parallel to the axis. These two are the necessary and sufficient condition for Hopf bifurcation. Now, for the spatio-temporal model, in this section we consider the roles of different factors affecting the species distribution on a spatial as well as temporal scales, by assuming that both prey and predator populations move randomly in the XY directions for their biological requirement. In fact, the prey-predator populations move randomly for their necessities, like searching of food, shelters, social interactions, etc. And after incorporating the effect of diffusion of prey and predator populations, our temporal models becomes this kind. This is the diffusivity coefficient ds, di, and dp. And here omega bar is the suitable spatial domain, and assume that at any time t and position this satisfies this. And this is the boundary conditions, Neumann boundary conditions, and this n hat is the unit onward, unit outward normal to the omega del omega bar. and del square is the Laplacian diffusion operator, and DSDI and DP are the coefficients of diffusion for the susceptible prey, infected prey, and predator populations, respectively. And for the stability analysis of this spatiotemporal model, we introduce both time and space dependent perturbations around the equilibrium E star, and the linearized system can be witnessed this way, and where this epsilon 1, epsilon 2, and epsilon 3 are positive and small constant, and kx and ky respectively are the components of wave number k along x and y directions, and eta k is the wavelength. Now, using this in the system in our previous one, spatiotemporal model, and ignoring the higher order, we obtain the characteristic equation, this, and this k square is, this is the wave, k is the wave number, is equal to kx square plus ky square, and we get the cubic equation in eta k. And employing the Routh-Hurwitz criteria, the spatiotemporal model is stable provided all these coefficients, this one, psi 1 k square, psi 2, and psi 3, all are positive, and this psi 1, psi 2 minus psi 3 is positive. And for the diffusion-driven instability, one of the following conditions must be satisfied. That's this one is negative, this one negative, or this one is negative. And finally, we have calculated that the sufficient condition for diffusion-driven instability is that if this psi 1, psi 2 minus psi 3 is negative, we have already calculated this one, that for the Turing instability, it is sufficient to show that this psi 1, psi 2 minus psi 3 is negative for some wave number k is greater or equal to 0, and we can write phi of k square in this way. And for our numerical simulation, this is the only for the temporal system. This first one, this one is the stable coexistence, and if the preference, this is the preference of predators on prey population, this parameter theta is higher, is 3.3, then this is the unstable coexistence. And for this higher value of preference parameter, and if this K1 is the level of fear responsible for the reduction in the growth rate of susceptible population is this, then we get the stable coexistence here. This figure is stable coexistence at the preference parameter theta, and K2 is the level of fear responsible for the eradication of the infected population, and this one is the unstable coexistence at lambda. Lambda is the rate of infection. That is, if the rate of infection is higher, we get the this unstable coexistence. And last one is the stable coexistence at this higher rate of infection, and as well as for lower rate of this parameter theta. That is, this theta is the preference of the predators. If this theta is lower than this one, that is previously it was 3.3 and now it is reduced to 0.53, then we get the stable coexistence. And this system This is for the temporal one. This is the unstable coexistence for R. R is the growth rate of predator due to additional food. And here we also get the unstable coexistence for gamma. Gamma is the recovery rate of infected population. And this is the bifurcation diagram for the temporal system with respect to K1. First one is for K1, that is for higher level of fear responsible for the reduction in the growth rate of susceptible prey population. Then the system bifurcates from stable to unstable. And this second one is the backward bifurcation for K2, that is level of fear responsible for the eradication of the disease prevalence. And third one is for lambda, that is the rate of infection. For higher rate of infection, the system bifurcates from stable 1 to unstable 1. And fourth one is the backward bifurcation, and this is for nu, and this nu is the crowding effect of the predator population. And this is the bifurcation diagram with respect to theta, that is if the preference of predators, preference of the predator is higher, then the system bifurcates, and we get similar results for gamma and R. And this is the two parameter bifurcation for K1 lambda. This K1 is the level of fear responsible for the reduction in the growth rate of susceptible prey, and lambda is the rate of infection. And this is the stable zone, and this one is the unstable zone. That is for lower rate of K1 and lambda. This is the stable coexistence, and for higher rate, we get the unstable coexistence. Here also, this is for K2 and lambda, and K2 is the level of fear responsible for the eradication of the disease prevalence and transmission rate. And this is for theta, K1 and theta. Theta is the preference of predators, and here it is K2 theta. And this is the biomass distribution of susceptible prey, infected prey, and predator population over time and space. And here we get that there is a non-homogeneous type of distribution. And we have actually explained everything. We solved the system numerically by using finite difference and Euler approximation method. And it is well known that spatiotemporal dynamics of a reaction diffusion system depends on the choice of initial conditions. And we have shown that spatial distribution of the population to interpret the model system in the spatial domain with the following initial conditions. And here A star, I star, B star, the components of equilibrium points. And this is the spatial distribution of susceptible prey. First one is for the susceptible prey, second one is for the infected prey, and third one is the predator population for different time scale. This is at the beginning. This is for t equal to 50 days and t equal to 1000 days. And parameters have the same value as in our previous one, only except that the diffusivity rate of susceptible population is higher. That is, this is now we have taken it as 30, and here it actually implies that this is the increase in the population density. And this one is the spatial distribution of susceptible prey infected and susceptible infected and predator population at different time scale for 10 days, 15 days, and 45 days. Here we have considered the diffusivity rate of susceptible population is very, very low, that is 0.203. And from this, we can say that the combined effects of fear, additional food, and selective predation in an eco-epidemic predator-prey system have been explored in the present study, and the model dynamics has been investigated in temporal as well as spatial settings. Our simulation results showed that if the rate of infection is very low, then the disease can be wiped out and only the susceptible prey survive in the system. Infection persists only when the disease spreads at a suitably higher rate and extinction of predator is observed for their higher mortality, while only predator persists in the system if the infected prey die at a higher rate. The level of fear responsible for lowering the growth rate of susceptible prey induces oscillation in an otherwise stable system. This indicates that a low level of fear responsible for the reduction in the growth rate of susceptible prey is preferable for dynamical stability of the ecosystem. In contrast, the strength of fear reducing the prevalence of disease potentially suppresses oscillation in the system and brought the system to a stable state. Whereas in our temporal system experiences hop bifurcation as the intensity of disease prevalence boost up. Thus, to avoid any dynamical complexity, one should focus on reducing the transmission of disease among the susceptible prey population. The intraspecies competition among the individuals of predator population also plays a vital role by returning the system to a stable mode from an unstable situation. And oscillation also appeared in the temporal system on enhancing the preference of predator on susceptible prey. Another important criteria is additional food to predator significantly changes the system's dynamics. It terminates the persistent oscillation and drives the system to a stable coexistence. Our simulation results showed that the diffusive system can give better result to different kinds of spatial pattern. Our spatio-temporal models generate inhomogeneous pattern. I have already mentioned of the susceptible prey, infected prey, and predator population over space and time, and setting the diffusion coefficient of susceptible prey at a higher value, while those of infected prey and predator population at lower values. We observe that our diffusive system demonstrates different types of patterns, such as combination of red and blue geometrical spots on the green background, yellow and blue spots on the green background, and third one is the butterfly-like patterns. As time flows, the densities of all population increase on the spatial domain. However, this is for when the diffusivity coefficient is for the susceptible prey population is higher. Whereas if the diffusion coefficient of susceptible prey is also low, initially we saw combinations of red, blue, and yellow spots on the green background, and finally disappear, and the predator density increases. And these are some references. And my collaborators, they have contribution for this work, Shashank Shekhar Maity and Dr. Pankaj Kumar Tiwari, and thank you.
Okay, thank you very much. Very good. Are there any questions?
What is the biological sense of that threshold A1, A2 minus A3 when this condition leads us to a locally stable solution? Is there any biological reason for that term?
Nouri, can you hear us?
Actually, it is not audible at all. Can you please?
So, do we need to repeat the question? Can you hear us? Excuse me.
Professor Paul, do you hear us or not? Can you hear us?
Yes, now.
Okay, finally, we're gonna repeat the question. Yes.
What is the biological reason of the term A1, A2 minus A3 when we get a locally stable solution?
Sorry, these parameters from the theorem, as I remember. So you had the theorem, and there was like few parameters. A1, 2, 3. Yes. Maybe this one.
And,
yes. So
are you talking about this one?
no, the previous slide. Yes, this one, the theorem. And the question is, what is the like biological meaning of this coefficients?
This one is for locally asymptotically stable. That is, the eigenvalues have negative real parts or they are negative. These are the necessary and sufficient condition of Routh-Harwich criteria that this one A1 positive, A3 positive, and A1, A2 minus A3 is positive. And in case of Hopf bifurcation, if this is equal to 0 and it satisfies the transversality condition, we get the Hopf bifurcation. Is it?
Yes, there is, but what does it mean in biological sense? In biological sense, what does it mean? A1?
Yeah. This first one, that is, if A1, A2 minus A3 is equal to 0, then if we put this here, we get one eigenvalue is equal to 0. One eigenvalue is purely negative, and other two eigenvalues are purely imaginary. This is the criteria for Hopf bifurcation. One eigenvalue is negative and other two are purely imaginary. And in that case, if this is the transversality condition, that is the tangent at this point means at the bifurcating point, theta is equal to theta bar, the tangent is not parallel to the axis. This one is the gradient.
Okay, thank you very much. Are there any comments? Maybe in Teams we have something. Okay, so here we should stop, and thank you very much for your lecture, Professor Paul. And now we have 5 minutes.
Thank you.
Thank you very much. And applause one more time. Professor Morales, are you here?
Do you hear me?
Yes, we can hear you. Hello.
But is your 5 minute?
Yes, we have 5 minute break.
Yes, you should be breaking, no?
So now probably start.
Okay,
sharing
tell me so a little bit to share. You will give me the opportunity to share the screen, isn't it? I mean, you will give me the permission to share.
Now you have a permission. You can do this.
Okay, I can do that now. Okay, I can. Okay, I will see how to share because it is. I appear.
Yeah. Yes, we can. Yeah. We can see you. Hello.
Hello.
And so it should be a button. I don't know where it is, like on
with 3 points. A button with 3 points.
Yeah. No, not the bottom with 3 points. It's like a rectangle with the arrow.
Rectangle with the arrow. Okay, I got it.
Like,
I got it.
You just have to move to the left, right? And near it is.
Perfect. I have a share a screen here. Permitir.
You cannot see
yeah, I push some button.
Yes,
what
now
happened?
we can see
now
your screen again.
Okay, but what is supposed to do? I will open my.
If you will open the presentation,
are you seeing?
see.
Are you seeing my?
We can see like all your screen. So
can you see? Can you see my screen? My screen.
Yes. Yes.
Okay. Can you see the title?
The title, yes.
Okay, so this is enough for me. Don't worry. And then I will do with this. Yes. Okay, so I will put a little bit bigger and start to talk. That's it.
Yeah, we have 2 minutes before we will start.
Yeah.
I will introduce you to the audience, and then we will start.
You should be drinking coffee now. Don't worry. Yeah. Relax. No problem.
Thank you.
Okay.
Dear colleagues, it is time to continue, and our next speaker is Mr. Morales. from Federal University of Rio de Janeiro, Brazil. Professor Maurer, stage is yours.
Okay, thank you, organizer, by taking me into account to give a lecture. Okay, I will. Can you see my screen now? No.
Yes,
It's
we can
okay.
see you. Yes, it's perfect, but yes, probably you should make it bigger.
Bigger. Okay, let me try to be bigger here. Maybe like that. Oh, wow. Okay. What about that? What about this?
It's perfect. Yes.
Okay. Okay. And okay. Today, what I want to talk is about this. What is a neural network, training, and so on. This is I can consider this an application of ergodic theory, little application of ergodic theory to this topic. Okay. First, okay, the content is this. I will introduce the perceptron, which is the minimal. It's like the minimal neural network, the smaller neural network. And some objectives, the iterative function system as a training. This is the novelty here. And the proof of the main theorem and continuous training, which is something which is incoming. No? Okay, let me put the introduction to this topic. The supervised learning in neural network appear when comparing output and giving input. You put in an input in a neural network, and you get an output, and you want to compare with the desired result. The error is propagated back through the system to adjust the weight. Okay, this is the idea. The network have some package which provide to seek how to make the propagation to convert to the ability to predict. This appear when the training process goes to stopping just when the system reaches on the desired accuracy. Okay. Okay, popular training here, propagation is given by optimization process like a gradient or stochastic gradient. Okay, there are, however, okay, those topics. Okay, when you want to compute the gradient or the stochastic gradient, you have to make a derivative. Okay, the problem you will do that derivative in the weights. And the problem is that the weights sometimes, the weights are not even real numbers, complex numbers. They may belong to some irregular set like a fractal. And this is the idea, what to do when the weights are not numbers in the usual way. They can also be belong to some manifold. But in that case, the gradient method still apply. Okay, but I'm talking about more complex situation when the weights are far from being possible to derivate, to do a derivative. And then the process is therefore natural to consider the weight to lighten a general metric space. Okay, now I will explain this. Okay, now and the present setting, the error function is given by and the problem is to find what we will call an efficient training for that error. Given an error, we are going to try to find that efficient training. Those are just iterative process carrying the initial weight close to the minimal error. And I will describe this situation in the perceptron situation. Okay, let me talk about the perceptron. What is the perceptron? This is a neural network. Very simple. You have the input vector, A1, A2, those are coordinate, the weights, W1, W2, those are, and the usual way is to produce this product. You have the bias, the B is an additional weight, which is the bias. And the one is the constant input number. Okay, you use this product. Okay, a little bit confusing here because okay, this part is supposed to be W multiplied by the vector I, which is formed by I1, I2 plus the bias. Okay? Then you do this proceeding and put an activation function, where the activation function is the usual, in this example will be 0, 1. This function represented by this symbol, which is, okay, 0 here and 1 here. This is the idea. And P is the value you obtain after the input, passing the input through that machine. Okay, this is the per second. Okay, the per second data is this. So as I told you, the target is the expected value. What do you want to have? In that case, 0, 1. The input vector is this, the vector formed by I1 and I2. The number 1 is the input component. It's an input component, but this is constant 1. And PI is the output for the given input vector. Is 0, 1, 2. W1 and W2 are the weights. They form together the vector weight, which is W1, W2, and B is the bias, okay, which is understood as an additional weight. Okay, well, what we want is to put the output to be equal to the expected value. This is what we want. I mean, in this per section, we are going to introduce here the input, and here the P is the result of the output of the neural network, and we want to compare with this target value. This is what you this is the appear in the case when you put you try to train a neural network in a way that he can identify, for instance, the picture of a cat or a dog. You have to train to reach this level. Okay. This is the idea. The output should be equal to the expected value t, and we need to weigh the weights and the bias, which is an additional weight. This means that in this situation, we are going to modify those guys, the W1, W2, and the B, in a way that when the result appear P equal the expected value T. This is the idea. Okay. Well, how to adjust the weights? This is the problem. Okay. The problem. Okay. How many ways we have to adjust the weights? Those ways will be referred to as training. In the present example, we can proceed. We are going to proceed with the following training. We are going to replace this is the all weights together with the bias, and here we'll put an alpha as a constant learning rate. This number. This difference t minus p times t minus p minus p is just the difference between the expected value and the output, which is precisely the error. Okay, this is the vector input vector together with the a constant number 1, which is the addition. This is a constant here, and then when you do this difference, you produce the new W and the new B. And the idea is you will do this process. You will from here, you will go to here, okay, and repeat the process in a way that in certain moment. The idea is to take the weights in a way and the bias until you reach this equality. Okay, this is the idea. Okay, the error is given by this. I told you. I mean, this is the error, and in the above up to date, we know that the error implies that there is no up to date. I mean, when you produce the error 0. Is that you have a fixed point in your training, which is in this case this training. Okay, this is the example now. Okay, I will do a small picture I get from the internet in YouTube. You can see this example. Okay, here the initial. You put the initial W's. The initial. Okay, the initial W 0, 0, 0. And the initial IB, the input plus the bias, you will put this situation 1, 1, 1. You will do the product with this weight until you get the number 1. The number 1 does in that case. Okay, sorry. You will get the number 0. The number 0 don't match with number 1. No match here. That's why it's no match here. And then you repeat the process. You will again do the process, but now with the new I and the new B. With those data, you will repeat the process. And here you get number 1, and it's supposed to be number 0, but therefore no match. And you repeat the situation with the new new I, new bias, and then you will see that in an example you match in this situation. You in the third attempt you match, saying you are right to the minimal error, which is 0 in that case. This is the procedure we do. We start with the IB. You enter with PI. This is this is exactly the output. Okay, and okay, you proceed. Then they can compute the error. Once you compute the error, you compute now you compute the today of the W and the bias, and then you repeat. You go to here and repeat the process. This is the training of the perceptron in that case. Okay. Now, our objectives. Our objectives in this lecture is to formalize the idea of efficient training. And second objective, we are going to give a measured theoretical characterization of those training. And at the end, I will talk about a continuous version of our topic. Okay. Now I will go to more details, mathematical details. Okay. Okay. First of all, we are going to consider a metric space W, which is usually compact. The error function will be a function from omega to R, which is bounded from below, and therefore you have a minimal value. I will assume the pre-image of the minimal value, which is sorry, okay. Which is the R mean. This is the usual standard notation for the minimal value, the preimage of the minimal value. We are going to assume this compact. And in SQL, we introduce some training we are going to deal with. We are going to do the training here will be considered an iterative function system, which we going to introduce now. The node Z0, the space of continuous map from omega to itself. And I will put this distance here, the traditional Z0 distance. Okay, here, because no compact, you have an infinity metric indeed. So you this notation, the distance between a omega and a point and a set. Okay. Okay, let me see something. Okay. Okay. This I will call this a global attractor of some certain map from omega to omega. If this is the distance between the iterator for f of omega to b go to 0 and go to infinity. The iterative function system generated by the node intercept C is given by this group. It's the semigroup of continuous mass generated by T. This is this is exactly this set. This is exactly the semigroup. Okay, the orbit is defined. You pick up an element and push along the orbit of the iterative function system. Okay, when we are going to specify better. Okay, how the orbit is computed. Okay, the asymptotic behavior of the orbit is computed by using this procedure. At the beginning, you have the orbit, which is a big set. Now you have to specify how the asymptotic behavior of the orbit is. Okay, this is done as follows. You pick up n0 equal the additive semigroup of non-negative integers, and you put the capital theta as the infinity product of our C, the generators. Okay, this is nothing else than the sequence of elements of C. Okay. Now I will keep this omega with this distance, which is a traditional, and since the C is compact, the product is compact also. Okay, this is keep it with the product metric. The shift is defined like this, and then you define a map from omega theta for omega theta by this formula. You pick up the omega. You go to this guy to omega 0, transforming omega 0, apply to omega, and the theta is up to date with the shift in theta. Okay. Now, now I will collect this projection. This is the projection in the first variable, okay? And the orbit is just given by this formula, which is not a big deal here. What the interesting thing here is precisely to introduce the pi, which is the projection, okay? Now I will define a global adapter for the iterative function system using the pi, the projection. I mean, this means the projection have the property that the projection points will go to convert to B. Okay? Then the iterative function system is in omega will refer to those will be the training. This is given, you see, the idea here is why this come from, where this idea come from? Come precisely from this consideration here. When you you have this training here, you see the today here. Today looks to be a map, but this map is indexed by I, therefore it should be considered an application 1 map, 2 map, 3 maps, which are necessarily different. Okay, that's the idea. They consider the training as a composition of maps. Okay, and that's in that way appear naturally the semi-group, and in that way appear naturally also the iterative function system, which is usually in dynamical system. Okay, and okay, and now that I will call the training will be efficient for the error E if the argmin is precisely the global adapter of the training. Okay, this is a definition. This is the main definition of the paper or the lecture. The training will be considered efficient when the iteration by the training will go to convert to the argmin, will go to convert to the minimal value of A. Okay, please, organizer, tell me how much time I have.
I think it's like 13 minutes.
30. 1, 3.
Yes.
Okay, perfect. Okay. Okay, let me check 1, 3. Okay. Now I will give some example. Now we only one generator. I mean, only one map in C in the generator set generating set C. The constant training. Those are constant map for some omega star in omega. It happened that it will be efficient training when the omega star belongs to argmin. Of course, this is not so not good in practice because the omega star. I mean, this is required to understand or to know what argmin mean will be, and this is usually difficult. This is precisely the training is about: is to find the argmin. Yeah, you will go to convert to the argmin. This is the idea of the training. So those are not so good, but those are useful, for example. Then this is a usual condition decreasing along the orbit condition. Therefore, do not imply that this is efficient training in general. Because you see, this constant map satisfies easy this relation, and then but it will be efficient only when the omega star will be contained in the argmin. Okay, you also can define stable trainings. This is the definition. I will not go into detail because of the time. Okay, but it's possible to try to study those guys, especially here the DC0. Here we are considering training with only one generator. But okay, I didn't define what is the distance C0 between iterative function system, but this is not so difficult to find to define using the generators. Okay. Okay, let's go to the gradient descent. This is also an example of this situation where you have the omega is a compact region, and this is twice differentiable convex, and with the Asian belonging to that interval, I mean bounded. In the sub condition, you get that this is the traditional gradient descent method. This will be an efficient training for some eta. This eta is very small, making this a contraction, the T, this map. And therefore, since a contraction will be easily seen that this is a training. Okay? Okay. Now, the idea, what I will go to do here is a measurable characterization of the training, the efficient training. For that, I have to introduce some probability topics. A volume probability measure is just a measure in X, in fact, metric take X, in the Borel sigma algebra, giving one index in the whole space. This set is denoted by mx, and this is a measurable map, and you can define the push forward measure. And this is a measure mu will be invariant under F if it's a fixed point for the push forward. Mu is ergodic when he takes value 0, 1 in the invariant measurable set. Okay. Now, this is for map. This is definition for map. Now, I mean, which are precisely iterative function system with one generator only. Okay, the training will be, okay, for trainings, this will be the invariant measure, which are mu for which the marginal of which are marginal of invariant measure of AT. The AT is, remember, this is the operator giving me for me the orbit. Okay, this means that the mu is considered invariant, is the projection or is the push forward of some invariant measure of AT. Okay, and then I will put the guilty everything in AT. Here, okay, this is the identity making the invariant measure, this identity. Okay, I'm trying to pick up, but no easy. This identity, okay, this identity is precisely I will define similarly the ergodic invariant measure for T are precisely given by this formula. Those are push forward of ergodic measure of the AT. I will put the guilty in AT in all situations. Then our main result is this: a training T of an error E of omega will be efficient if and only if the integral of the E on the ergodic measure gives to you the minimal value A minimal. This is the main characterization I have in this direction. Okay, I will give a continuation of this result also. And okay, there are some examples here. The first example is the constant training, which you can apply this formula here. You can apply, and you will see in that case the Dirac measure supporting omega star will give to you the formula if and only if the omega star will be is in the R min. And this is precisely the conclusion in example 1. Okay. You can apply also in ergodic optimization, which is the Olivier Jenkinson topic. This is the problem of This is the problem of finding for a given compatibility space omega T a given function, a given error, a mu star ergodic realizing this minima. Okay, this is, you can see that we know this equality is true, and therefore the efficient training are precisely those with one generator of A are those T maps for which this minimal ergodic value is at the minimizing ergodic invariant measure. Mu is equal to A min. So this can be, our approach can be applied to the situation of ergodic optimization. Okay, let me go quickly to the proof of the main theorem. This will be consequence 3 lemmas. The first is because we have a characterization, and here for maps, not for iterative function system, or this is for iterative function system with one generator only. Then this will be a global attractor of F if only if this is equality 2. If the R min is a global attractor, then you have the equality, the desired equality, right? This is not so difficult to prove. You pick up this is a consequence of a Birkhoff ergodic theorem, and okay, this very easy to prove this lemma, not so difficult. And the second is ergodic decomposition theorem. This is traditional. I picked this version from Santiago paper, but you can find also in the Volpert book. Okay, this is the ergodic decomposition, means that a measure you can split into ergodic component, the quality, in a way that the integral over from continuous function is just the integral over the sum of the integral of the ergodic component. This is for every continuous L1 function. Okay. The next lemma, okay, I will consider the sufficient, but only for one generator only. Okay. This is a consequence of the ergodic decomposition. Okay, you suppose that 3 is 12, but argument is not. This is a contradiction proof. And then you get the distance between these. You will have a phase sequence for which this distance is bounded away from 0. Okay. Then this is the same. You have the iterate of omega 0 will be bigger than this this quantity for a given delta. Okay. When you define this sequence, this is the empirical measure, the Dirac measure supported along the orbit. You consider this sequence, and because omega is compact, you have this. This is compact with respect to the weaker star topology. And this topology, I will remind to you that this topology is given by this convergence. This is the topology corresponding to the weak convergence in the linear operators. So it very give to you the desired capacity. Okay, this will go then the sequence mu k will have a convergence subsequence, and then you will do some computation involving the definition precisely of the definition of the convergence in the weakest star topology. Okay, then you will this formula, and then you apply the ergodic composition. You will have this is bigger than this value, and then for some element ergodic measure, you will have this inequality, which is precisely contradicting the assumption. This is complete the proof for you, and then this is the proof of the theorem. Okay, the proof of the theorem is now to translate the whole thing to the iteration function system. That means when the generators are not only one function, and you do this through this this new error, you define a new error. Given the error you will have to control this new error. This new error transform to you the problem to one generator only situation. And okay, this gives to you one. Precisely, this is the trick. So I will not go into detail because of the time. Okay, the continuous training will be similar. For semiflows, indeed, this required to be a new structure, call it multi-flow system or something more in deep. But here I will stay in semiflows. This is a semiflow approach is given is nowadays very used in the Wayman E approach about the neural network, which is a continuous time. Okay, but okay, here you consider this continuous training, which are precisely semiflows, and I will consider the training to be efficient when this training converts to the attractor. The mean is a global attractor of the flow. Okay, okay, you have the traditional invariant ergodicity and body probabilities invariant measure, and then this is the training, the theorem C, which is at the continuous training T, is efficient for the error if only if you have this inequality too. Okay, this is now I will present some reference here, including the very nice exposition by Santiago of the ergodic decomposition of invariant measure. This is the traditional book, etc. This is the Olivier Jenkinson approach of ergodic optimization, and this is very famous book by Boyd and okay. Thank you very much.
Okay, thank you very much. Are there? Oh, first we should applause to our speaker. Are there any questions? Well, actually, I have a question. Maybe could explain why do we need exactly continuous error function? Maybe, so, or maybe we can consider some different functions.
Oh, okay. About what? Can you repeat the question?
Why we consider Exactly, continuous function, error function.
Why continuous function, error function? Yes, this is a neural network situation. The error used to be the difference between the expected value and the output. Power some power, usually square. It may also be the integral in some LP space, depending on the situation. Yeah? Depends on the situation. Maybe maybe this situation can be pushed to LP also, but I didn't. Okay, yes, perhaps it's a good idea to push this situation to LP, to some L space. Yes, I agree. Okay. Okay, it continues here because it's a topological approach rather than a measurable approach. Yeah. Okay.
Okay, sorry.
Uh-huh.
It could be of LP class.
Yeah. Yes. Here, the approach looks to be the ergodic decomposition and those tools are true also in LP spaces. So here can be pushed to LP situation too. Yeah, but continuity is used in some moment. In some moments, use the continuity. But measurability plus Lucene theorem maybe overlap the situation. This is something I have to think better, because continuity, I use continuity in some moment of the proof. Yeah, but theoretically, you can consider as a training as any function. I mean, this is theoretically possible, but to get results, it's better to put some regularity, no?
Okay, thank you so much. And are there any questions? Maybe something online? No. Okay, so thank you very much.
Thank you to you.
And now we have a break. It's like 20 minutes. Пожалуйста.
Good day, my name is Michael Khristichenko, and first of all, I would like to thank the organizers of the conference for the possibility to make this talk. And my talk is about computation and tracing of stationary solutions of the Marchuk-Petrov model. Systems of delayed differential equations are widely used as models used to study the dynamics of virus infections and immune response. The Marchuk-Petrov model is one of such models. The non-trivial stable stationary solutions and stable periodic solutions to this model can be interpreted as chronic forms of disease. To study these conditions of existence of such solutions and parameters of their stability, efficient numerical algorithms that for searching in the multidimensional space of model parameters for parameter values that correspond to such solutions with the given characteristics are required. In this talk, I will briefly describe our technology developed in these works for tracing, for computation and tracing of stationary solutions of time-delay systems, and present and discuss the results of tracing and computation of stationary solutions of the Marchuk-Petrov model with the parameter values corresponding to the hepatitis B infection. The talk is organized as follows. Firstly, I would like to briefly describe the Marchuk-Petrov mathematical model of antiviral immune response. Then I will talk about the algorithms of computing and tracing stationary solutions, and then I will present the results of computing and tracing stationary solutions of the Marchuk-Petrov model. It should be noted that nowadays there is a software package DFDE tool which implement different algorithms for tracing stationary solutions and periodic solutions and analyzing this stability for systems with delays of more general forms than models of virus infections. However, the problem of guaranteed computation of all stationary solutions of the models is not considered in this package. So we're trying to create a new technology that will allow one to compute all stationary solutions as the values of their parameters, of the model parameters, and analyze their stability. And we intend to use this technology to investigate different chronic forms of diseases and to investigate the possibility of constructing the optimal disturbances that transfer system from the states corresponding to the chronic forms of the disease to the state of the healthy organism. The Marchuk-Petrov mathematical model of antiviral immune response is formulated in the form of a system of nonlinear delayed differential equations. This system describes the rate of change in the concentration of viral particles, virus-infected cells of the target organ, destroyed cells of the target organ, antigen-presenting cells, macrophages, T helper lymphocytes of the cellular immunity, T helper lymphocytes of the humoral immunity, T killer lymphocytes destroying virus-infected cells, B lymphocytes, plasma cells producing antibodies, and antibodies. Using this model, the quantitative regularities of the dynamics of acute human infections by the influenza A viruses and hepatitis B viruses were studied. Unlike the influenza, the hepatitis B has, along with the acute form, different chronic forms, different in the level of the viral load, degree damage to the liver cells, and the intensity of the immune response. It should be noted that the study of the chronic forms of diseases using the model of such complexity as Marchuk-Petrov model has not been performed before. Denoting the vector of this system by this vector and vectors of the parameters of the system by P, we can write down the system in the following compact form. The stationary solutions of the model with given values of the parameter are non-negative solutions of the following nonlinear system of algebraic equations. The solutions to the system with the fixed values of the parameters can be computed by the methods of computer algebra implemented in the unsolved procedure of the Mathematica package after reducing this system to the system of four equations. The numerical study of dependence of the stationary solutions of the model on a parameter is conveniently performed by parameterizing some curve in the space of the vectors of the parameters, and we denote the parameter of this curve by S and the interval of its variation by eta. Also, we denote by F the left side of this equation, and as f is a rational function of its variables, this set is a part of a real algebraic variety. And the task is to break this variety into irreducible sets of this form, and the points at which this equality falls as in the neighborhood of such points. This equation does not define U as the unique implicit function of S by the implicit function theorem. So to construct these irreducible sets, we construct the grid in the interval eta, and we compute all stationary solutions with the unsolved procedure in each node, and we will call these solutions exact solutions. After that, we trace stationary solutions from each node to the next one by the standard ODE5 numerical integration procedure based on explicit fourth and fifth order Runge-Kutta methods applied to the numerical solution of the initial value problem of the following form. And then we refine obtained approximate stationary solution by exact ones. If exactly at the if step of the algorithm we consider the interval SE and S from SE to SE plus 1, at the node SE and SE plus 1 we compute the exact stationary solutions by the unsolved procedure. They are denoted by the circled points. And then we trace a stationary solution by a solution of the initial value problem, and we stop the integration if the parameter S reaches the value of SE plus 1, this squared point, or if the mentioned determinant turns out to be integration trajectory at this squared point. Then we refine obtained approximate solutions by the exact ones. This is denoted by this curve. And then if some exact solutions are not obtained by the approximate, by the solution of the initial value problem, we trace these solutions from the value of SE plus 1 to the value of SE to this squared point. And in the end, we connect these stationary solutions into the irreducible sets. Using this technology, the stationary solutions of the Marchuk-Petrov model were computed. This table shows the values of the parameter of the Marchuk-Petrov model corresponding to the acute hepatitis B infection. So in the first task, we traced stationary solutions on the antigenic stimulation rate constant of macrophages in a lymph node. By varying this parameter, we vary the strength of immune reactivity at the level of antigen presentation, and we trace this, we varied this parameter in this interval. This figure shows the dependence of stationary solutions on the parameter, and the stable, the solid line corresponds to the stable stationary solutions, and the dashed line corresponds to the unstable ones. So, as we can see in this figure, for these values of the parameters, there is 4 stationary solutions, and only one of them for some values of the parameter is stable. And it loses its stability up to some value of the antigenic stimulation rate constant of macrophages in the lymph node. And this means that for the big values of this parameter, there is acute form of the hepatitis B, and for the small ones, there is a chronic form of hepatitis B. For systems that describe the dynamics of virus infections and immune response, it is of primary importance from the point of control strategy to find the domains in the space of in the parameter space where the system is multi-stable. It's exactly where 2 or more stationary solutions of the system is simultaneously stable. The described technology allows one to obtain such domains. For example, we decreased the secretion rate constant for particles of HBs antigens by 1 hepatocyte per day, and we traced these stationary solutions along the same parameters in the same interval. And we obtained this picture, this figure that shows the dependence of stationary solutions on the parameter. And as we can see here, there is 2 stable stationary solutions for these values of the parameter, one with the high viral load and one with the higher viral load. That can be interpreted as a chronic form of the disease, and one with the state of the healthy organism. One with this one with the 0 viral load, which can be interpreted as a state of the healthy organism. It should be noted that this result coincides with the theoretical results. In this work, the condition of asymptotic stability of stationary solution with a 0 viral load was given, and here it is. And as is shown for the original values of the parameter, this condition is not fulfilled. The stationary solution with a 0 viral load is unstable here. And for after we decreased the secretion rate constant of HBs antigens by 1 hepatocyte per day, this condition was fulfilled, and as we saw, here the stationary solution is stable. The stationary solution with a 0 viral load is asymptotically. And finally, for the third task, we decreased the synthesis rate of constant of IgG molecule by a single plasma cell distribution rate constant of infected hepatocytes due to the cytopathy of viruses, and secretion rate constant for particles of HBs antigen by 1 hepatocyte per day. And we increased rate constant of destruction of hepatocytes by cytotoxic T lymphocytes, stimulation rate constant of cytotoxic T lymphocytes, and we also changed the function C of M to increase the sensitivity of the immune system to the destruction of the target organ. And we also write the same, we trace the stationary solution along the same parameter in the same interval. And in this figure, the results of tracing the stationary solutions on this parameter is shown, and in this figure, the enlarged right part of this interval is shown. And as we can see, for these values of the parameter, system is monostable for some values of the parameter, if exactly there is only one stationary solutions which is stable, and there is values of the parameter where system is B-stable if exactly there is two stable stationary solutions. It means that by varying the antigenic stimulation rate constant of macrophages in a lymph node, we can transfer the system from one stable stationary solution to another. In conclusion, I would like to tell that in this talk, a technology for computing and tracing of stationary solutions of systems of nonlinear delayed differential equations, which are actively used in modeling of infectious diseases in humans and animals, was presented, and with the help of this technology, for the first time, for the Marchuk-Petrov model of antiviral immune response, conditions which were parameter value domains for the existence of stable stationary solutions corresponding to chronic forms of the hepatitis B were computationally found. Thank you for your attention.
Thank you very much. Let's applause to the speaker. Are there any comments or questions?
In your solution, you require a function to be analytic in reals. That is a very strong assumption. Are there any ways to weaken that requirement, or can you even consider some non-smooth solutions to the system?
I guess you talk about this function, yes?
Yes, you require u of x to be analytic. That is a very strong assumption, and in nature there aren't so many naturally arising functions which are that smooth. So can you weaken the requirement, for example, have it a finite number of derivatives, or maybe even can it be discontinuous or non-smooth from Lebesgue or Sobolev spaces?
I really don't think that this is a restriction to our algorithm, but of course, for now we look only in smooth solutions, as we for now, for this model, we didn't find such solutions that wasn't so smooth, and maybe it will be done in the future.
Thank you. Are there any comments and maybe questions? Well, actually, I have a question. Your system looks really complicated. And are there any attempts or maybe some motivation to find out some solutions?
Uh,
Or maybe for some restricted system?
Can you repeat the question? You said that we
Is
have,
it,
yeah.
is it possible, or are there any attempts to construct some analytical solutions to this?
Not stationary solutions. The
No,
other
stationary,
solutions.
but I mean analytical.
Analytical,
as a formula, like.
Yeah, understand. No, I don't know of such attempts to construct the analytical solutions, and of course, as in the beginning, we tried to find such solutions as the formula, and for this system, we reduced this system to the system of two equations, but the equations are too complex to find the analytical formula of the solution.
Okay, thank you so much. Are there any other questions? Okay, so let's applause one more time. And please take your certificate. Thank you so much. So we have a 7-minute break. Yes, it should be there. Always control.
Okay, okay.
So now we should continue. And our next speaker is Professor Fahimi from Semnan University, Iran. Please, the stage is yours.
Okay. Hello, everyone. Good afternoon. Let me briefly introduce myself. My name is Milad Fahimi, and I'm a PhD of Mathematics and Semnan University from Islamic Republic of Iran. And I'm delighted to be here today to talk about a hybrid stochastic fractional order coronavirus mathematical model via the reservoir-people transmission network. My presentation is divided into three major parts. The first part is devoted to the stochastic differential equation of our model, and then fractional stochastic differential equation as a hybrid form, and finally numerical simulation for illustrating results. Let me start with some general information about my talk. As you are all aware, as you know, mathematical biology is one of the most interesting research areas, especially for applied mathematics. In these researches, modeling of infectious diseases are considered as an important tool to describe the dynamic of epidemic transmission. One of the common way for analyzing the dynamic of COVID-19 as a important disease is use of differential equation. Let me start with some general information and preliminaries. In our study, we suppose that omega, f of t, and p be a complete probability space with a filtration f of t satisfying the usual condition. We also let R with dimension d and d-dimensional stochastic differential equation that we see in this slide. I think I'd better summarize due to the lack of time. And finally, we suppose m-dimensional standard Brownian motion defined on this probability space omega, f of t, and p. Also, f and g are locally Lipschitz function in X. We define the differential operator L associated with equation 1 that is described in a previous slide, as you see in this slide. And if L acts on function V, we can obtain this equation that you can see in this slide. And briefly, the generalized Ito formula implies that this equation that is famous for all of us. Now, this slide is devoted to construct the main part of our lecture. In this work, we consider a mathematical model for COVID-19 transmission dynamic. This model consists of 6 variables. This model consists of 6 differential equations named as a reservoir-people model. This model is a simplified and normalized form of BATS host, reservoir, and people model, BHRP model. Assuming SP and EP refer to the number of susceptible and exposed people. IP denotes the symptomatic infected people. AP denotes the asymptomatic infected people, and RP denotes the removed people, including recovered and dead people. And W denotes the COVID in reservoir, for example, the seafood market. These variables have the unit of number which are considered as at the time T. Also, the model parameters and the definition can be seen in the next table, in next slide. In this table, we can see model parameters and their definition. For example, NP, capital N, the total number of people that we study in sample. Small NP, the birth rate parameter of people, MP, the death rate of parameter people, beta P, the transmission rate of IUP to SAP, and beta omega, the transmission rate from W to SAP, and so on. I think I'd better summarize it. This table can show us the model parameters and the definition, and so we construct our model. The process of normalization is implemented as follows. SAP is equal SAP over NAP, and so on, where NAP is the total number of people, the normalization of our model, the normalization process of our model. In order to provide additional degree of realism, we define the environmental noise and Brownian motion and propose a stochastic model. As you are all aware, I think it's better to say that one of the common ways for analyzing a dynamic of COVID-19 is to use ordinary and stochastic differential equation. One of the main benefits of STEs or stochastic differential equation is that they allow the validity of assumption to be tested statistically and produce an estimate with additional degree of realism. However, there are times when stochastic models cannot truly received and compared with expectation, but they are useful to have more accurate estimation. So white noises made the parameters involved in the system often fluctuate randomly. In this part, for example, NAP changed to NAP plus sigma 1, beta 1 of T. BAP changed to BAP plus sigma 3, B3 of T, and so on, where BIT and sigma I for I equal 1 to 6 are Brownian motion and the intensity of white noises respectively. So we can present the following modified model with a stochastic approach for COVID-19 with 6-dimensional view or approach. The next session is devoted to dynamical analysis of solution. In this session, existence and uniqueness solution of introduced model to, the stochastic differential equation of our model and the equilibrium of system are presented. The first theorem prove and demonstrate that the coefficient of a stochastic differential equation number 2 are locally Lipschitz. And the second theorem prove and demonstrate that for any given initial value as seen in this theorem, there exists a solution, SAP, EP, IP, AP, RP, and W of T for model 2, and the solution will remain in R positive with 6 dimension with probability 1. This slide is devoted to equilibrium of the system. Equilibrium of system can be estimated by setting all derivatives equal to 0, as you are all aware. In order to obtain the fixed point of COVID-19 model, we consider the first derivative of SAP equal to 0. We obtain SP tilde as you seen in this slide, and so on for EAP, for derivative of EAP, and for derivative of IAP, and all 6 derivations. So we can obtain to the equilibrium of system in next slide. In order to achieve biologically relevant solution, we find equilibrium points such that this system have positive solution because we work in mathematical biology. To find this is free equilibrium of a model, we consider the point S tilde, E tilde, I tilde, A tilde, R tilde, and W tilde, which implies E equal this point that you see. In this is free equilibrium point, the population of 5 compartments, you see 5 compartments of categorized people tend to 0. And the system can be recognized in healthy situation. The situation can be recognized in a healthy situation. Therefore, the Petrov fractional order of system can be described by using Caputo-Fabrizio fractional derivatives as follows. It is essential to note that I ignore to explain about the basic definition of a CF or fractional, stochastic fractional and fractional derivative because the lack of time I implement the operator Caputo-Fabrizio fractional derivative as you've seen in the model. On the other hand, one of the most considerable characteristics of COVID-19 is its different behavior in various countries and regions, or even different individuals, which can be sign of certain and accidental behavior in the disease. We believe that a stochastic model established by our work can be useful for researchers in making informed decisions and taking appropriate steps to dominate the COVID-19 disease. Various benefits can be obtained from a fractional order system in the sense of best data fitting and about its memory and to identify the best possible value of fractional order can be best describe the model for real phenomena and other cases. In addition, it makes the model constructed in fractional derivatives more strong and useful for describing real phenomena. In epidemiology, FDE or fractional differential equation is utilized in real phenomena and in order to analyze the COVID-19 infection and to provide a better understanding of disease dynamic. So we construct the fractional stochastic form of our model. This slide is devoted to extinction of disease. In this session, we established sufficient condition for the extinction of disease. In order to form this condition, we consider variation in the number of symptomatic infected people, and we have already the deterministic model, the basic reproduction number are 0 as follows, that you've seen in this slide, where psi and psi prime is shown in the end of this slide. In deterministic epidemiological model, basic reproduction number is planned to be a criterion or index of transmissibility of infection agent. If R0 greater than 1, then the outbreak is expected to continue. If R0 less than 1, then the outbreak is expected to become extinct. In this stochastic COVID-19 model, we consider the effects of high-intensity white noise on the prevalence or extinction of COVID-19. So we present a theorem. Let this point be the solution of model with initial value that you see in this part. We obtain limit supremum of ln of I of t over t when t tend to infinity. Furthermore, if the assumption this one and delta p greater than 1, if this assumption holds, then I of t will tend to 0 exponentially with probability 1. So this theorem demonstrates the extinction of disease. Theorem 4 shows that the disease will decay exponentially to 0 under suitable conditions when the noise sigma 2 and sigma 5 are sufficiently large such that this condition holds. The disease goes extinct exponentially. The white noise sigma 2 and sigma 5 are related to the fluctuation of MAP, the death rate of people, and delta P, the proportion of asymptomatic infection of people respectively. And finally, simulation results. I think I'd better to summarize it.
You have 2 minutes.
2 minutes, yes. In this session, we get a deep insight into the dynamical behavior of our model. For numerical simulation, we use Euler-Maruyama method, and we consider the following discretization model for this discretization form that you are all aware, as you know. I briefly, I should explain about this one. According to the World Health Organization, WHO, reported reported an incubation period of COVID-19 between 2 until 10 days, and the United States Center of Disease Prevention, CDC, the mean incubation was 5.2 days. So we use this real data in our model for simulating and estimating. After this numerical simulation, as you've seen in this figure, I think I'd better to summarize some details. The strength of our presented numerical method is particularly demonstrated in our figures, as you see, which show that the adoption of our model with real data and deterministic model, as you've seen in this slide. On the basis of simulation, figure 2 shows that the number of symptomatic infected people, IOP, will decay to 0 under suitable condition presented territorium 4. Therefore, numerical simulation confirmed the effect of high intensity white noises on prevalence or extension of COVID-19. Thanks for your attention.
Thank you very much. Applause to the speaker. Other questions or comments?
I'd like to thank you for an interesting talk. I have one question. Does this model take into account vaccination rates? Vaccination rates, vaccines.
In this model, we don't implement the effects of vaccination. Some models have studied this effect. We don't implement it.
Thank you. Are there any questions?
Excuse me, because this model is constructed before starting vaccination.
I have a few questions. First is, it was a theorem where you showed that the coefficients are Lipschitz. Are the assumptions? No, before. The first, I think it was the first theorem. Yeah, but what is the assumptions why we should prove this? Can we just assume that it's just Lipschitz, or have you misunderstood something?
That's an interesting question, but because of the lack of time, I summarize it. I recommend and suggest you to read our read the details in our article. I think it's
okay,
better.
Thank you. And would you please show us? Maybe it was one of the last theorems with coefficients sigma 1 and sigma 2. What is where the parameter goes to 0? So what is the meaning of parameters sigma 1 and sigma 2?
These are intensities that are implemented for having a stochastic environment that we define it here. Sigma 2 and sigma 5.
But what it means, I know, biologically, or just a random parameter?
It means we must have a little fluctuation about these parameters. If the noises was high, it doesn't work. The intensities of this stochastic form is important for us.
What are the noises?
Noises used to construct a stochastic differential equation. If we have them, we can construct them.
So it corresponds.
White noises.
So what it corresponds to what?
What's the benefit of them?
Okay, maybe.
Yes, they help us to have more accurate and more exact model, because COVID-19 have a lot of parameters, and if we have them, they can help us to have more accurate models.
Okay, so maybe I just should ask you to send us some papers about this. Okay, thank you so much, and let's applaud the speaker one more time. Okay, and Professor Fahimi, here's your certificate. And we done for today. See you tomorrow.